Hey there, chemists. In this lesson, we are going to look at orbitals, which are locations of where you might find an electron. And you'll notice right away on your notes, I see pictures of different orbitals. They have names and different shapes, and they're actually arranged about the nucleus, and they tell us where electrons are located. I want to animate this first and show you a quick video. This shows the 1s orbital. That's the shape of the orbital coming into level 1. Energy level 2 also has an s orbital, but it also has different sublevels called p orbitals. And there went one of the p orbitals called the px. Here comes the py orbital. And there's a third one, the pz, oriented along the 3 different axes of a coordinate system. Then the third principal energy level, level 3, also has s electrons. It also has p orbitals, p electrons. There's the 3px, 3py, and here comes the 3pz. You should notice it's larger than the 2p orbitals. They are larger and they're in a higher energy level. There's the 4s, significantly larger than the 3s or the 2s. And once you get to level 3, you also get the possibility of what are called d orbitals. You'll see in a moment there are 5 different types of d orbitals arranged in different spaces around the center of this 3-coordinate system. These look like balloons, but they are mathematical solutions, sort of like clouds, of where we are most likely to pinpoint and find an electron. And that's what that picture is meant to show you. So let's write down a few things about this and look back at our notes. Here are pictures of the 4 different types of orbitals. They are the s, the p, the d, and then there are also f orbitals. Those respectively stand for sharp, principal, diffuse, and fine. You don't really need to know that for the purposes of this class, but that's what those names come from. And they can hold certain numbers of electrons and only exist in certain shells. Now, the s orbital looks like a sphere. It can hold up to 2 electrons, and you have s orbitals in every main energy level. So there is such a thing as a 1s orbital, there is a 2s orbital, there is a 3s orbital, etc. They are quantized in specific principal energy levels, but we get them at every single one. The next set, the p orbitals, there's 3 different types in any given subset, but they don't start until energy level 2. So we don't have a 1p orbital, but we do have a 2p orbital, a 3p orbital, a 4p orbital, etc. And each one is capable of holding 2 electrons. That's true for any individual orbital. It can only hold up to 2 electrons in it. There are 3 of them in the subset of the p's in any principal energy level. So I'm going to write 6 electrons next to it, because that's how many I can get in one set of p orbitals in a principal energy level. Below that, we get to the d orbitals. There are 5 different types of d orbitals, and at 2 electrons each, that means we can get 10 electrons. And the d orbitals don't start until level 3. So we can't have a 1d or a 2d, but there is such a thing as 3d, 4d, etc. And lastly, the one that we'll see probably the least often are the f orbitals. And you can look at the picture and notice there are 7 f orbitals. At 2 electrons each, that means I can get 14 electrons in a set of f orbitals, and they don't start until level 4. So I could have 4f, 5f, etc. There's actually orbitals beyond that as well. You just go down the alphabet past that. There are g orbitals and even h orbitals for excited states or just other situations. We're not going to see that too often in this class, but they do exist, so if you see them later on, don't be too surprised. Now, where are the electrons arranged? Well, they follow what's called the Aufbau principle, where you can imagine them occupying the orbitals from the lower energy states to the higher energy states. So we would fill electrons in the 1s, followed by the 2s, followed by the 2p, etc. And there are diagrams that help teach students how to follow this. Here's one that goes from the upper left diagonal to the upper right diagonal to the lower left. As you work your way down, just this list of different orbitals. I prefer to teach students how to just use the periodic table, which is already set up in a way that reminds us where the electrons are arranged. So here's a periodic table on your notes in front of you. And notice the first 2 columns are 2 columns wide, and they kind of stand out from the rest of the table. That is what many of us call the S block, as opposed to the middle section of the periodic table, which, if you count, happens to be 10 columns wide. They call that the D block. d orbitals can hold up to 10 electrons. S orbitals can hold up to 2. So that's not just a coincidence. This is a very useful way of figuring out the electronic arrangement. All the way on the right, we get to the p block, which happens to be 6 electrons wide. This particular one is not including the F block. The F block falls right in between lanthanum, hafnium, actinium, and rutherfordium. It's right there, and if you ever forget, you can just look at the break in the atomic number changes. We go from 57 to 72. You jumped 14. So go look at a periodic table and find the F block, which is down below it usually. That just makes it fit on a piece of paper more easily, but it actually is right in the middle of the table. You can imagine parting the columns and shoving it in between those two spaces, and then you get a very long periodic table from left to right. But that's where it actually belongs, and it's 14 columns wide. Now I want to label a few other things on this periodic table before we learn how to use it. Let's go ahead and number the rows from top to bottom. I'll number the hydrogen 1, below it 2, then 3, 4, 5, 6, and 7. And what that does is it tells me this is the 1s block, this is the 2s block, the 3s block, etc. And s starts at level 1. Let's number the other rows in the middle of the table, but for each block. Where does the d electron start? D doesn't start till level 3. So this is actually, I'm going to squeeze this between calcium and scandium. This is the 3d row. This is the 4d row. This is the 5d row and the 6d row. And let's go over to the p block. P starts at level 2, so let's number that. This is the 2p row, the 3p, the 4p, the 5, 6, and even the 7p section of the table. And what we've done is we've isolated different parts of it, and we can just read this left to right, going down the columns as if it's just a novel. And as you get to the element in question, you find that you've recited the electron configuration along the way. Let me show you what you mean. Let's start with scandium. Scandium is right there, number 21. It has 21 electrons. And if I look at the sections of this table that I go through on my way from hydrogen to scandium, let's just read out loud. I would get through the entire 1s block, which is actually only 2 columns wide. Sometimes people actually put helium way over here because it technically is an s block element, but it makes more sense over here with the rest of the noble gases, doesn't it? So we usually see it over there. Regardless, that's 1s, and I went across 2 rows, so I'm going to say 1s2. And then I get to 2s, also 2 columns wide, so 2s2. Then I get to 2p, 6 columns wide, so 2p, 6. Then I get to 3s, 2 columns wide, 3p, 6, 4s, 2, and 3d, 1. And I just recited the arrangement of the electrons from beginning to end. So let's write that out. We had 1s2, 2s2, 2p6. I'm just looking at the periodic table as I write this down. Then we get to 3s2, 3p6, 4s2, and then 3d1. Now those numbers in front, those look like coefficients. They represent the principal energy level. And you should notice that 4 is the highest one, so the valence electrons of scandium are actually in the 4s level. I just write it this way because this is how the periodic table reminded me where they exist. The superscripts show the number of electrons in each sublevel, and if you add them all up, you should get 21, because that's how many electrons are in scandium. So let's just do that. 2, 4, 10, 2, 4, 10 more, that's 20 and 21. It works. The superscripts always have to add up to how many electrons are in that species. So what would it be if, let me box out where scandium was. Let's just show it because we did it for scandium. What would be different about iron, which is just a few columns over from that? Well, the beginning is going to be exactly the same. All that's different is the end of the configuration. The 3D subshell will have 1, 2, 3, 4, 5, 6 electrons in it. But everything else is identical. The core of iron is the same. So we get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, what did we say, 6 electrons over. So it's only the end part that's different. And we'll find that that's the most useful thing when we're looking at electron configuration, is what's the last bit look like? Because those are the electrons that are typically involved in most chemical reactions that we're going to study. We can also do an electron count if we want to, just to make sure. Iron is 26 electrons, and if you add up those superscripts, you get 26. What about phosphide? This is phosphorus with 3 negatives, so let's find phosphorus. There's phosphorus with 15 electrons, but remember the 3 negative charge means it has 3 more, so it actually looks like argon. So if I write out the configuration of argon, I would have 1s2, 2s2, 2p6, then 3s2, 3p6. That should be the 18 electrons in phosphide, the anion of phosphorus. And you'll notice it hit a noble gas. It has the same electron configuration as argon, so we can abbreviate this with the symbol for argon inside a pair of square brackets. That doesn't mean it's the same as argon. It has a different nucleus, but it has the same electron arrangement as argon. We call that isoelectronic, same electron configuration. And this actually brings up where we can use this noble gas shortcut technique to simply write out the electron configuration of any element and its core, and then just tack on the valence. So I could have done that for both iron and scandium. I could have written argon followed by the rest, and that's equivalent, and it certainly saves time. So what would it be for cesium? Cesium is way down here in the 6s row, and its electron configuration would look like what it is for xenon, the noble gas I passed most recently, with just 1 extra electron in it. So I can write xenon in square brackets, followed by 6s and then 1 electron. That would be the entire configuration for cesium. How about iridium? Iridium is a little bit past cesium. We get it down here. That has 77 electrons in it. Now careful, this passes the F block, which we mentioned earlier is in between lanthanum and hafnium, and you can always remember because of that atomic number jump. So I'm gonna hit an F block, and it's gonna be the 4F. It's gonna be the first one. If I had an F block on this table, it would just be 2 rows. It'd be the 4F and the 5F, because that's where the F's start. So how do I write that? Well, let's start with the noble gas. It would still be xenon, and then I would hit my 6s2 electrons. Then I would technically hit 5d1. Then I would hit the 4f14 down here, and then some more 5d electrons, which I hit with iridium. So let's write that out, and we'll see what it looks like. So it's going to be xenon, 6s2, technically 5d1, followed by 4f14, and then the rest of the d electrons, 5d. Let's check how many more after that gap. Well, it looks like we have 6 more. 1, 2, 3, 4, 5, 6 more. So you could write it as 5d6. It's a little confusing to break up those d electrons. They're in the same subshell. So we're just going to consolidate those d electrons into one 5d7. And it's actually a little arbitrary if you want to put that at the beginning before the 4f or after it. Frankly, the valence electrons are the 6s, because that's the highest principal energy level. Lastly, let's just look at bromine. Bromine is higher up, I believe. Yes, there it is, right before krypton. Now, we can't use krypton's configuration if we want to use the noble gas shortcut. The lower noble gas that we actually filled is argon. So this is going to be argon, followed by 4s2, 3d10 all the way across, and then 4p5. And you can always do an electron count. Bromine, neutral bromine, is 35 electrons. Argon is 18. So we have 18 plus 17 more. Yep, that's 35 electrons. That works. Your superscript should always add up to the number of electrons that the species you're describing actually has. Okay, the last thing to wrap up this lesson is to talk about what are called orbital diagrams. This is just a different picture of describing what we just wrote out, and it helps us understand some of the periodic trends that we're going to come into in future lessons. Orbital diagrams are just visualizations of these orbitals, but they're drawn very simply as rectangles or just sometimes horizontal lines, and an electron is simply abbreviated with an arrow, a vertical up or a vertical down. So hydrogen's configuration of 1s1, I would put 1 electron in it. Helium is 1s2, and they go in opposite directions when they pair up in the same orbital. Lithium is 1s2, 2s1. I'm going to keep going over to the right. Beryllium is 1s2, 2s2. Boron, we're just adding 1 electron each time. 1s2, 2s2, 2p1. Then I get to carbon, and now I am, for the first time, looking at multiple electrons in a given sublevel, and here's what happens. 1s2 occupies like so, then 2s2, and then the first 2p electron goes there. The second one actually goes in the unoccupied orbital. This is like getting on a bus in the city. You're going to occupy any seat you want when they're all empty. But as soon as you're sitting somewhere, someone else is probably going to sit in their own unoccupied seat before sidling up next to you. That's just a little socially awkward. Electrons are the same as people. They will fill orbitals singly first before they have to pair up, which means if I have something like fluorine would be 1s2, 2s2, and then 2p5. 1, 2, 3. Uh-oh, the fourth electron has to pair up, and so does the fifth electron. This is called the Pauli exclusion principle, combined with Hund's rule. Excuse me, this is actually more Hund's rule, where electrons occupy orbitals singly first before they have to pair up. The Pauli exclusion principle says we can't have any more than 2 electrons in an orbital, and you can't have an electron with the same quantum numbers as another electron. We'll get back to that in a later lesson. So I'd like you to just try the last few. What would the orbital diagrams look like for potassium, titanium, copper, and chromium? And then come back and check. Just hit pause and fill those in and see how you did. Okay, so potassium, I'm going to look back up at the periodic table. Potassium is number 19. It ends with 4s1. So really that's the most important part, which means everything else is just completely filled. 1s2, 2s2, 2p6, 3s2, 3p6, and it gets a little tedious, doesn't it? So you can also use the noble gas shortcut for this. The noble gas that we passed most recently prior to potassium was argon, so you could also write potassium as bracket argon, and then just a horizontal line with the letters 4s below it with 1 electron in it. That is also acceptable for potassium in terms of the orbital diagram, because it's really only this valence part, the outermost part, that's most important. So I'm not even going to bother with titanium and copper and krypton. Actually, let me get back to copper and krypton in a second. Titanium, if I find that, that's 3d2, so I simply have to add, let's see, it is 4s2 and then 3d2 singly. Copper and chromium both fill up argon. That's really what argon is. If I want to highlight that, I should really just draw it across the core noble gas. That's argon, 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 and then the rest. Now copper, if you look at where copper is on the periodic table, it is 1 shy of finishing up the D block. It would be, I would think, 4s2, and then 3d should be 9. However, ground state copper actually looks like this. It looks like 3d10. This is an exception simply to know. I'm not going to go into why. There's lots of arguments about why this is, but copper is one of 2 exceptions to know. It's easy to identify because it completely fills the d orbital. So there's only 1 unpaired electron, and it's 4s. and the rest occupy the 3d. That actually makes a little bit of sense because 4s technically is the valence orbital, so it kind of makes sense that that would be the last one that stays unoccupied. Chromium is the other exception to know, so this is really exceptions to know. It's these two. I would think that chromium would be 4s2 and 3d4, but it actually takes one of those s electrons and it goes in the d, so you get a completely half-filled 3d orbital. Okay, so that shows how we write orbital diagrams for the elements using the electron configuration, which for the most part you can use the periodic table to figure out. This one, if you zoom way in, even shows you the valence configuration of the elements, and you can even see some of the exceptions that we just mentioned. In fact, you'll notice it's not unique. There are other exceptions in the d block where it's uniquely stable to have a completely filled d orbital. That's one explanation that's been offered to identify this. We're going to come back and look at orbital diagrams some more and eventually get into how the electronic structure is what really dictates how these things react.